Welcome to the lectures on evolution of air interface towards 5G. So, we are discussing the main unit of waveform in the 5th generation, and that is the numerology. We have explained the frame structure earlier, and in the previous lecture we have described how the numerology's subcarrier spacing is to be designed and why it is decided in such a manner, and when all did this work start and what is the genesis and the original source of work, which you may find useful towards understanding more details or even coming up with better designs which can be useful in future generation communication systems. So, we will briefly very quickly look into the background. We simply stated that there is variability of Doppler conditions, and beyond that we also stated that Doppler spread leads to intercarrier interference. We had explained the orthogonality loss, where signal power decreases, interference power increases, and we said that since the mobility conditions are different, and in case of Doppler, instead of a single frequency shift, there is an entire range of frequency which comes in. So, even if there is good CFO tracking algorithms, it is limited in its effectiveness, and ICI cancellation mechanisms are also very complex, and especially when there is a whole lot of Doppler frequencies, the effect of such mechanisms are no longer useful. We also identified that the intercarrier interference power, which is due to the Doppler frequency spread or phase noise, is affected by parameter which is the ratio of the offset or maximum offset with respect to the subcarrier spacing. So, if there are situations where we are unable to reduce this, that means we are unable to control this, because this is a natural phenomena, you are unable to control, and one would not like to do ICI cancellation, then the denominator parameter is under your control and becomes a design parameter. And we have proposed that this could be used flexibility as per the situation, and what we find happily is that the 5th generation system is actually using such a mechanism which can provide very simple way of accepting this broad Doppler spread or phase noise related issues which can give rise to ICI. We have also explained how the system works visually. So, when there is offset, there is reduction in the signal power, increase in interference power, but if we make the denominator larger, we find that things can be improved significantly. And we have also presented some of the results by which we have shown that as the subcarrier spacing increases, that means as the FFT size decrease, and the subcarrier spacing increases, we find that the wider subcarrier spacing are useful for more velocity or larger velocity, or in other words situations where phase noise is larger, whereas they are not good under situations where Doppler is less or phase noise is less. So, what we find is that if we have a combination of different subcarrier spacing which can be brought about by choosing the number of or the size of FFT, one can effectively cover the entire set of Doppler or phase noise, or effectively the frequency offset or frequency spread, by adaptively choosing the subcarrier spacing. And there you get a huge amount of benefit, up to 30% benefit in spectral efficiency can be found based on the investigation that we have done. Based on newer settings, even one can find more precise numbers which are available for the 5th generation. We also iterated that such systems can be implemented in the frequency division manner, in a way that a large bandwidth can be split into smaller sections, each having let us say 20 megahertz or 10 megahertz or 40 megahertz as per availability, and they can use different subcarrier spacing. And the detailed ways of how this assignment can be done are also mentioned in the references which we have pointed out. We also had said that such mechanism may be implemented in time division manner depending upon the implementation strategy, and similar benefits can also be fetched. So, this particular picture we had shown where we said that mixed strategy can be used, and the worst condition or the extreme case is where an absolute mix of different spectrum, different subcarrier bandwidth can come into play, where this picture particularly gives the time frequency diagram. This is the time and this is the frequency axis, how it would look like, and what would happen because of the interference. So, some kind of orthogonality loss is introduced because not all subcarriers are orthogonal, but you can choose a set of subcarriers which will be maintaining some kind of orthogonality amongst them. So, when we have a group of subcarriers, they will be orthogonal to each other. However, one set may be orthogonal to another, but it is not in the reverse direction. So, there is some kind of orthogonality loss, and we have found that the edge subcarriers which are at the edge of interference would be suffering the most, but still you can benefit a lot. We have also shown implementation mechanisms which are also very vital, and we had also shown how at the base station side various things can be, various subcarrier spacing can be introduced, while they can be decoded at the user end independently, and the reverse direction they can be generated independently and combined at the base station receiver side. So, we have also presented different architectures and we have provided the benefit. We have also given you the references which we find are important, which you can go through for finding more details. Now, we move on to the other aspect of the numerology, that is the guard interval or the cyclic prefix, and we will discuss how this is to be chosen, so that together one can find ways to select both the subcarrier spacing and the guard interval, so that one gets to an appropriate combination of choice during deployment. So, in this particular picture, although it is from some papers, we have taken it only for academic reference. You can always find reference to these particular papers. It is shown that the delay spread has a certain distribution, and in this picture, which is again from one of the works by Vinko Arcek, we have shown, or we have actually taken it from there, which shows that as the distance increases, the delay spread also increases following certain distribution. So, effectively what we mean is that when you, instead of looking at a situation where delay spread is constant, rather one should take delay spread as the characteristic of a particular environment. Now, when we look at the deployment scenarios, what we have described earlier is that there are various deployment scenarios like indoor scenarios, urban micro cells, small cells, rural large cells. So, if you look at these different conditions, the amount of echoes and multipaths and their characteristics will be different. So, if they are different, then we naturally expect in some environment the delay spread to be maybe symbolically in this manner, in another situation it might be symbolically like this, and in another situation which is like this. So, it effectively means that there are larger echoes coming at longer duration of time, whereas in other cases this is smaller one. So, the same air interface has to handle multiple situations. So, what happens is one would design an air interface. So, I will redraw it here, a small, a medium and a large. So, if one has to define an appropriate air interface, then the cyclic prefix interval should be chosen as large as this, because this is tau max over all possible deployment conditions. But what we find is that if the channel impulse response is small, in certain cases there is a huge loss in spectral efficiency. So, all we are trying to do is find out mechanisms by which this can be improved. So, we can actually reduce the cyclic prefix length, that is what is the proposal. So, what we find is that in case you reduce the cyclic prefix, whereas you encounter a situation where the channel impulse response is large, in that case you would encounter irreducible inter-symbol interference and there is significant degradation in performance. So, effectively one has to find an appropriate balance between the two conditions. That means, neither one can use a very large cyclic prefix that would reduce the spectral efficiency, and if one uses a small cyclic prefix, then one would end up in a situation that where cyclic prefix is large, there would be ISI. And this kind of ISI is irreducible, you cannot reduce it by simply increasing the signal power. So, this leads to the obvious choice that can one make the cyclic prefix dynamic? Okay. Can this be made dynamic? The answer naturally is yes, one can make it dynamic, because the cyclic prefix is not connected to this subcarrier spacing, right. Cyclic prefix is not connected to the useful duration of OFDM symbol. It is only connected through the spectral efficiency, because the spectral efficiency would be the ratio of useful symbol duration divided by total OFDM symbol duration. total OFDM symbol duration is useful symbol duration plus guard interval. Now, if we find cases where guard interval becomes pretty large, then whereas the useful symbol duration has not been modified, then the OFDM symbol efficiency decreases. So, one way to improve the OFDM symbol efficiency is to increase the useful symbol duration part. So, if you increase the useful symbol duration part, then the entire fraction becomes larger and the efficiency increases, right. So, if I increase the OFDM symbol duration, then in other words I am affecting the subcarrier spacing. So, the only way it is connected, not through the characteristics of the channel, but because of the efficiency factor, one can think of associating TCP with TU, not otherwise. So, summarizing, we find that the frequency spread, which is indicated by del f, one can think of putting a suffix c indicating with respect to carrier, is largely due to Doppler or phase noise, and Doppler is largely due to velocity or mobility or due to the carrier frequency, whereas the tau max is with respect to deployment conditions. That means, it is dependent upon the multipath scenario, that means sigma tau or tau max, okay. And this affects your TCP, whereas this affects your capital delta F SC, which in turn affects your TU. So, there are two different things which affect these two important parameters of numerology, but if we take OFDM symbol efficiency, then we can connect these two. So, we can connect these two via OFDM symbol efficiency. So, if the OFDM symbol duration is becoming small because of this Doppler or the phase noise, then one can only reduce the guard interval, but up to that much only where tau max is still captured within the guard interval. So, we will see further some of the important outcomes of this. So, in this particular picture, we had depicted earlier that what are the different deployment scenarios. So, as we have shown earlier that in the frequency domain, one can divide the entire available bandwidth into smaller chunks, and in each chunk one can operate an OFDM system, and each can be of different subcarrier spacing, and in each one correspondingly a different amount of cyclic prefix may also be used. So, this is in frequency division, and this is precisely the way the 5th generation NR is operating, and we had also talked about doing it in time domain, which is open for implementation. So, this way one can appropriately handle the different variations and vagaries of the wireless channel in a very effective manner and use very low complexity signal processing at the transmitter, maintain the simplicity of OFDM. So, to do this, one has to choose the appropriate value of cyclic prefix. So, what we had presented over here is that the choice of cyclic prefix or guard interval can be done in an approximate way in some manner, although this is open for improvements, is that this particular guard interval should be greater than in some complicated function which involves the RMS delay spread of the channel. Now, RMS delay spread of the channel is something which one can measure or pre-estimate. So, this is one single parameter which characterizes the delay properties of the channel. We will see it again. It is also dependent on the signal to noise ratio required or SINR required, which is from the QoS conditions and which decides the modulation, code rate and BER. So, it is interconnected to these parameters, which is connected to quality of service. So, a particular BLER or BER for a given modulation and code rate is connected to the SINR requirement. So, it is also a function of SINR required, and we had also introduced a delta SNR indicating some margin, which is a bit different from standard thinking. That means one can partially trade off the cyclic prefix with respect to extra amount of signal to noise ratio, because it may be possible that the user end or the base station has some spare amount of power. So, we just try to figure out that if that extra amount of power could be utilized towards trading of some amount of ISI that may be present. For example, if one is choosing QPSK constellation, in that case, since there is only phase to be identified and not amplitude, there is certain margin what one can use. But if one extends to 16 QAM, then probably the margin that is available would be less. So, depending upon particular situations, certain amount of extra margin may be available to take care of the extra benefit by which can be achieved by using a different or variable amount of guard interval. So, these are all the parameters that we had identified. Along with this, TF, which is nothing but our TU, it is not the T frame as per the 3GPP descriptions, and which is equal to 1 upon delta F subcarrier spacing, is also one of the important parameters while taking a decision of the guard interval. So, if one computes such an expression and one may scale this RMS delay spread depending upon the particular power delay profile, one can scale this value instead of using it just like that to find an exact or more appropriate choice. But however, this will give you certain numbers, and since the CP is quantized, since only fixed values as you have seen 0.29, 0.57, 1.17 and so on microseconds are there. So, any value in between that this result can throw up, one can always go to the next immediate higher value of cyclic prefix that is allowed in the standard. So, in this manner one can also choose an appropriate value of guard interval. One can even simplify this, and what we have also shown over here, there is a parameter epsilon, which is again the ratio of delta FC by delta F subcarrier spacing. So, if one has information or prior information, then one can also introduce into this expression to get an appropriate value of guard interval, because this causes certain amount of interference, while the small guard interval, if it is used, also brings in certain amount of interference. So, there is a certain trade off between the interference or exchange that one can think of, how much one wants to distribute here, how much one wants to distribute there, and to find an appropriate size of guard interval. Although not entire thing can be exchanged, but partially it can be handled, because any ISI that is resulting over here would also result in additional amount of intercarrier interference. So, there is a complicated relationship amongst these parameters, and we have been able to find one particular expression through which one may be able to choose the appropriate choice of CP. Using the choice of delta FSC, we had earlier mentioned that the ratio epsilon is usually desired to be kept at more than 0.02. It should be kept greater than 0.02 to maintain 20 dB of SINR. Accordingly, one can fix up all the set of parameters for an operation. So, a choice of this together with TCP, and that has to map to an appropriate value of mu, one would get a numerology that needs to be deployed in the operational conditions. So, with this we summarize or we conclude the discussion on choice of parameters for numerology, although we will present a few results immediately following this. So, this particular result shows the overhead reduction by changing guard interval by allowing certain amount of extra SNR. So, what we see is that if a certain amount of extra SNR is allowed, so here reference is 15 dB, whereas 0.5 dB if extra SNR is used, or 1 dB or 17 dB, then we find that up to 60% of reduction in guard interval is possible. So, this particular set of results are with specific set of conditions which we have described in the references. One is encouraged to go into the references. And here what we have shown is the distribution of throughput. So, what we show is that the variable guard interval or variable CP OFDM, it can enhance the throughput by 20% or so, or one can get even better depending upon the operational conditions. So, by both the mechanisms, cyclic prefix can give you around 20% increase and the subcarrier spacing can give you around 30% increase. Now, together they may not add up to 50%, they may also depending upon situation, but that is the different amount of gains that can be benefited by using variability in these two parameters. Okay. So, these are the certain set of references which are very critical in this context. So, one again can find all details as discussed over here to understand how these different choices are made. So, here this particular picture essentially summarizes this can also be found in one reference from Ericsson also, they have given a similar picture. So, we have taken reference from that and recreated this, where we summarize the entire situation, where we say that on one side as the frequency increases, the operation frequency increases, phase noise increases, so does Doppler spread increase. So, one can think of this axis as the Doppler spread axis or phase noise axis or delta FC axis, and this one can think of as the tau max axis, and as we have said from earlier results because of other measurement campaigns, that this happens when the cell size also increases, right. So, when your cell size increases, tau max increases, and hence the guard interval required would increase, and to maintain the efficiency of the OFDM system, the numerology has to decrease, because decreasing numerology means subcarrier spacing decreasing and TU duration increasing. TU duration increasing means OFDM symbol efficiency increasing. Whereas, on this side we find that as the offset increases, the subcarrier spacing has to increase and hence TU has to decrease, right. So, this is the reverse trend. So, one has to choose a combination, this is a reflection of different combinations that one can get appropriately with methods as has been described in the earlier slides. Now, we quickly look at another important aspect, this link adaptation thing we had explained in an earlier lecture, which we do not want to discuss much now, but we just have it here so that you can take it as a reference and recall the earlier discussions that we had and continue on the next part of the discussion that we are going to have now. So, we had said earlier that the OFDM communication system in both the 4G and the 5th generation, they do not allocate one subcarrier. So, this is a subcarrier unit, this is the resource element, any one tiny box is the resource element, this is a subcarrier width, this is the time width, and this forms one OFDM symbol. Okay. So, this forms one OFDM symbol, all subcarriers 1 unit of time. And we had also explained that these different OFDM symbols, consecutive symbols and different subcarriers forms a resource block, which we had also described when we talked about the frame structure. So, now we also mentioned that in this resource block, the modulation, coding scheme and the power controls power is kept constant, and that is the unit of allocation of a particular data block or a particular user allocation. We had also mentioned that in the 5th generation, this size remains constant in terms of number of OFDM symbols, which is also same as in the 4th generation, that is 12 or 14 depending upon whether extended cyclic prefix or normal cyclic prefix. But because in 5th generation and what we have explained in the just previous slides, that the duration of the OFDM symbol would be different, that can become smaller or larger, hence the tile size is going to be different. Now, what we need to look at is a detailed understanding of the propagation characteristics. So, we had talked about the propagation characteristics, that the signal strength fluctuates significantly in the time domain as well as it fluctuates in the frequency domain. We can clearly see how in the frequency domain the signal strength fluctuates and how in the time domain the signal strength fluctuates, right. And we had also stated that this was in seconds, this is a larger window in frequency, whereas if we zoom into that particular picture and see a much smaller window, what we will find that when time is given in milliseconds, that when we zoom into it, there is much smaller variation in time, it is nearly flat. you can clearly see there is slight variation, where indicated colors indicate the signal strength, whereas still in the frequency domain we have a certain amount of fluctuation. Now, these fluctuations are dependent on two important parameters. One is the coherence bandwidth and another is the coherence time. Coherence time tells us the time duration over which the signal strength would remain more or less constant, and coherence bandwidth would give us the bandwidth over which the signal strength would remain constant in the frequency domain. So, now if the channel is having very high Doppler condition, then TC is low. So, if del f d is high, then TC is low. Similarly, if tau max is high, then BC is low, and vice versa and reverse. So, if it is low, then it is high, and if tau max is low, then this is high, and there can be other combinations also. That means, there can be cross combination, that means, this is high and this is low, and the other, that means, it is tau max is low and FD is high. There can also be such conditions because of the propagation scenario. So, now when you have this, if coherence time is small, the signal would fluctuate faster in time, and if coherence bandwidth is small, signal would fluctuate faster in frequency. So, in frequency there will be much faster fluctuations, in time there will be much faster fluctuations, and if the coherence time is large, in time domain it will fluctuate slowly. If coherence bandwidth is large, in frequency domain it would fluctuate slowly. So, that is what is going to happen. So, now what we will discuss is what is the effect of such a thing on different tile size. So, one can increase the tile slice or number of slots for allocation in time domain, or one can do the same in frequency domain, or one can do the same in both the domains. So, basically what we are talking about, how much of time window and how much of frequency window are to be grouped together to form a resource block in order to get the best benefit in terms of spectral efficiency. Okay. So, we will see such an effect. We first show the result when if you allocate a larger window in the frequency domain, that means more number of resource block, and do modulation, coding scheme and power on that window. So, here what we say is, suppose we group 64 subcarriers together, okay, we get a certain spectral efficiency versus SNR curve. If we reduce the subband size to 8, that means smaller window, then we find that the spectral efficiency increases much beyond that of 64. Now, this is the case when there is low diversity condition. Low diversity condition means that the signal strength remains flat over a certain window in frequency and over a certain window in time. That means, one can do link adaptation over smaller chunks of our concern, and chunks you cannot make lesser than certain numbers. So, we have said that this number is 12 in case of LTE and in case of 5th generation. We had done the study for the entire range from 8 to 64. We are presenting here only 2 extreme results. So, all other results would come in between. We are showing only 2 results for the sake of ease of seeing these things, right. Now, if we compare this particular scenario with another situation where the diversity is high, what we find is that there is not much effect of changing the block size in the frequency domain. Now, why does it happen in this manner? If we go back and try to discuss and look into this, if there is lot of fluctuation in time domain and lot of fluctuation in frequency domain in this small size, that means this window is already getting the effect of averaging the time and frequency fluctuations, and one calculates the modulation and code rate to be used as per this fluctuation. If you increase this size, the average over this entire size has not changed, and hence there is not much of a benefit. Whereas, on the contrary, if one would look at a situation where one would see that over this window there is a certain signal strength and over this window there is a certain signal strength. That means, the signal is fluctuating slowly in frequency as well as it is fluctuating slowly in time, let us say. So, that means over such a window we find that there is some flatness, a particular modulation coding rate to be chosen, whereas the other window one can choose a different modulation and code rate while satisfying the individual BER constraint. This is very, very important. So, this falls directly in whatever we have discussed when we talked about link adaptation. That means, each block is to be adapted so that the BER threshold is met. You can go back to the discussion on link adaptation as we had discussed earlier and refer to that particular discussion for clarity on this particular part. So, what we find is that when there is high diversity condition, there is no benefit. So, if we understand the channel well, then we can adaptively choose the slot that we can aggregate in time domain and the slot size that we want to put in frequency domain or number of resource blocks that we want to allocate. So, the immediate next result in the time domain, that means, if we extend it in time, is what we are going to show over here. So, this is link adaptation per 0.5 millisecond and this is link adaptation for 1 millisecond, for 2 millisecond and so on and so forth. So, as you increase the interval over which you are able to adapt, what you find is that the throughput is decreasing, or reverse way, as I do it faster, I am able to get a much more benefit in spectral efficiency. Whereas, when we are doing it in a high diversity condition, that means, within the duration of time for the smallest unit of block size, there is sufficient fluctuation in time domain, the averaging effect is already captured. So, the gain or change is not significant, whereas the overhead that will come in signaling the smaller units of tiles would be significantly large. So, here again what we see is that under low diversity condition, smaller chunks of tiles are going to give you benefit. Under high diversity condition, larger chunks of tiles are going to give you the same benefit without much modification. The last piece of result which we want to show is that one can think of even having very large code block size and putting different modulations in them. So, that means, we are suggesting that one can think of keeping the code rate fixed, but one can take chunks of data within that code block and vary the modulation index, instead of choosing coding and modulation scheme for each block which is different from another block. So, this will save a huge amount of complexity at the transmitter and receiver side, while it is going to give you some benefit. The benefit is what we will see. So, this red one is where you adapt the power, the modulation and code rate for each particular chunk that we are doing the link adaptation. But this result is the case where we have a certain code rate and you are varying only the modulation. So, what we see is that one can get a much more benefit by using even a single code rate without much of an effect. So, what we see is that if one chooses only a single code rate, but varies the modulation, one can still get sufficient benefit. Okay. So, overall what we see is that there are different combinations of schemes that are to be used and which are also supported in the 5th generation, and these are some of the references which describe all the details of these different mechanisms by which one can actually get this get all the benefits of having various adaptation in terms of subcarrier spacing, adaptation in terms of cyclic prefix, together called the numerology, as well as one can get all the benefits of link adaptation by appropriately clubbing a number of resource block or by clubbing a number of slots together to get the most benefit in order to maximize the spectral efficiency. In all this context, we have identified the resources which are primary in this kind of work, which have been one of the earliest kind of work and which describes all details that are presented in these different technologies and which are of use in the 5th generation communication techniques. Thank you.